This lecture video covers Chapter 2. The focus of the lecture is to review basic chemistry so that we will be ready to discuss macromolecules and their structure and function next week. This topic slide will be at the beginning of each presentation to let you know what you get to look forward to learning about, and it will also tell you what you should know and be able to do by the time we are done with the unit. So starting off, biology is the study of living things, and what we know is that organisms are composed of matter. That means that it is anything that has mass and takes up space. Please remember that we are not adding any matter to the earth. We are just simply recycling what has always been here. All matter is made up of elements, and compounds have two or more different elements. They will be combined in a fixed ratio based on their properties, which we will see later. And remember that the characteristics of the compound will be different than the characteristics of the individual elements. The example shown to the right is table salt, or NaCl. The properties of salt are very different from that of its components, sodium and chlorine. 20 to 25% of the known elements are considered essential elements. That means that organisms have to have them in order to be able to survive and reproduce. We notice that the percentages of those essential elements will be similar among organisms. 96% of all living matter is made up of carbon, oxygen, hydrogen, and nitrogen. The rest, like calcium, phosphorus, potassium, and sulfur, and other trace elements, are required, but those will be in minute quantities. So although we need those things, we don't need a whole lot of them, but we do need a whole lot of carbon, oxygen, nitrogen, and hydrogen. This is a breakdown of the human body and the percentage of each element that is there. So we're all mostly oxygen, and then followed by carbon and so on. The bottom part, that 3.7%, those would be the trace elements that we need, but not a lot of. With that in mind, let's focus on the structure of atoms. So an atom is the smallest unit of matter that retains its properties. It is made up of neutrons, protons, and electrons. The protons and neutrons are together in the atomic nucleus, which will be at the center of the atom, and the electrons will move rapidly around the nucleus, as you can see here. The diagram on the left, is just showing the electrons in a cloud because they are all the time moving. But then the one on the right shows it's paused, and those two little dots represent the two electrons of that atom. The atomic number is how many protons an element has, and this is going to be different for each element. Atoms have a neutral charge unless you see a superscript plus or minus. Its mass number is the total number of protons and neutrons because the mass of each electron is negligible. You will notice that the atomic mass will be close to the mass number because protons and neutrons are very close to 1 Dalton, which is the unit that is used for the atomic mass. All atoms of an element will have the same number of protons, but some may have more neutrons. When that happens, we have what is called an isotope. So those will be the different atomic forms of the same element. And in nature, we see a mix of isotopes around. For example, on Earth, we can find carbon 12, 13, and 14. We will also find radioactive isotopes where the nucleus will decay spontaneously to give off particles and energy. We can use radioactive isotopes in medicine, like for tagging things, and then being able to do scans and figuring out if there's a problem. And then we also use them for radiometric dating to determine the age of fossils. And with that, if you remember half-life from chemistry, that's how we can talk, or that's how we can calculate that. We will talk more about radiometric dating when we get to our natural selection unit later in the year. Energy is the capacity to cause change. So in atoms, electrons vary in the amount of energy they have. They have a lot of potential energy, which is the energy that matter possesses. Electrons' potential energy comes from their distance from the nucleus. So here we can see electrons, if you remember, are found in different shells, and they can only come to rest when they are in a level, but they very quickly will move between levels because it is unstable for them to be between. So as I said, electrons are found in different shells, and each shell has a characteristic average distance from the nucleus and energy level. There are also only a set number of electrons that each shell can hold. The chemical behavior of an atom is determined by the distribution of its electrons. And our periodic table of elements shows the electron distribution for each element. Of course, this is just a small segment of that. What we want to focus on is the valence electrons, which are the electrons found in the outermost shell. Each atom wants a full outer shell, and that tells us how the elements will bond. For chemical bonding, atoms will either share or transfer its valence electrons, meaning covalent and ionic bonds. Those are the strongest chemical bonds, and we'll talk some about the weaker interactions in a minute. Covalent bonds happen when two atoms will share their valence electrons, and it will either be a nonpolar covalent bond where electrons are shared equally, or a polar covalent bond where electrons are not shared equally. So we have slight positive and negative areas on the compound. An example of this would be water. In ionic bonds, one atom takes an electron, and the resulting positive negative attraction is what creates the bond. So cations are positively charged ions, anions are negative, and when we have ionic bonding, they're called ionic compounds or salts. This is an example of the formation of a covalent bond on the left, and then on the right is an example of a polar covalent bond in water. So we can see that on the oxygen end of water, we have a slight negative charge. And then on the hydrogen side, we have a slight positive charge. We'll talk more about the specifics of water in chapter 3. We're looking at its specific properties. But what gives water some of its properties is this slight negative and slight positive regions on the molecule. This is an example of ionic bonding. So here we have sodium and chlorine. Sodium is going to donate one of its electrons to the chlorine atom, leading it to be positive and the chlorine to be slightly negative, and then that attraction is what pulls them together. With the donation of that electron, both atoms now have a full shell of electrons. In biology, we will also be talking about some weaker bonds that are essential. Most importantly for our discussions are hydrogen bonds, where the partially positive hydrogen atom is attracted to a different electronegative atom that is close by. And this will almost always be either oxygen, so when water molecules are hydrogen bonding together, or nitrogen, as we see in the case of holding the two strands of DNA together. The other type of weaker bond is called the van der Waals interaction. And that's just weak attractions between molecules or the parts of molecules that result from local partial charges. So the regions where it's slightly positive or slightly negative. We will mostly be discussing hydrogen bonds. A molecule's shape and size is key to its function, and we will see that more next week when we talk about our organic molecules. The shape determines how biomolecules will recognize and respond to each other. As an example here, opiates like morphine and naturally produced endorphins have similar effects because their shapes are similar and they bind to the same receptors in the brain. So if you look at the diagram on the right, there is an area that is boxed in for endorphin that is produced by the human body and morphine. And since those regions are identical, they are able to bind to the receptor that that shape can fit in the brain. So, structure and function are super important, and we will talk more about that next week.